We shall look at the applications of Newton's second law to inclined planes here. Problem 1. Two masses are held on frictionless inclined planes as shown below. So this mass m1 is 3 kg and m2 is 2.5 kg. They are connected via a massless string through a massless pulley. Now alpha 1 is 30 degrees and alpha 2 is 60 degrees. Now when you let it go, the system will start to move. Now we want to determine the tension in the cord and the acceleration of the system. So let's begin with the free body diagram for mass 1. There should be two free body diagrams because there are two masses. And let's start with the first one. So what are the forces that is acting on mass m1? So this is the free body diagram for mass m1. Now note that this angle here is alpha 1 and alpha 1 is given to be 30 degrees. So the forces are as follows. So you have the obvious one, which is the weight of m1. Since the mass is 3 kg, the weight is 3 times gravity. And then of course you have the tension in this cord. It's going like that. You have the normal force from the plane, let's call it N1, and this weight has two components. There is the weight component parallel to the plane, and there is this weight component perpendicular to the plane. From our previous video, we have shown the component of weight along an inclined plane is given by the original weight, the entire weight that is, 3g, times the sine of the inclination angle, in this case alpha 1, which is 30 degrees. Likewise, the component of weight perpendicular to the plane is given by 3g cosine 30 degrees. This is what that contributes to the acceleration in this problem. So these two forces have been labeled here. Before we start to label the acceleration of the system, we have to know in which direction the system will move, whether it's going to move like that or like that. Which one is it? To determine that direction, let's compare the component of that weight of these two masses along the planes. So let's label that component of weight of m1 along the plane, which we have already computed there, W parallel 1, and the component of weight of m2 along the plane as W parallel 2. W parallel 1 is 3g sine 30 degrees. That is this number. W parallel 2 will be the mass m2, so the weight is 2.5 g times sine of alpha 2, because m2 is resting on a plane with inclination angle alpha 2, so that is 60 degrees. Now obviously the component of weight parallel to the plane of m2 is greater than the component of weight parallel to the plane of m1. So W parallel 2 is greater than W parallel 1. So that means the entire system will move that way, and that is also the direction of acceleration. So back to the free body diagram of m1, the acceleration must be labeled in that direction. Now let's write down Newton's second law. The net force equals ma. The net force on this mass m1 along the plane has got to be this minus that, because the acceleration is in that direction. Of course, the normal force and the component of weight perpendicular to the plane does not contribute in this case to the acceleration. So tension minus 3g sine 30 degrees. But we know, according to Newton's second law, net force equals mass times acceleration. The mass of m1 is 3 kg and acceleration is a. So we have the first equation to work with. 3a equals t minus 3g sine 30 degrees. Equation 1. So the first equation has been written down here. Now let's look at the free body diagram for mass 2. Now as you can see, mass 2 is in that plane. So what are the forces acting on this mass 2? As before, there is its weight. Since the mass is 2.5 kilograms, so the weight of this mass 2 is 2.5 g. Now there is this inclination angle of 60 degrees that we need to pay attention to. Other than that, we also have the tension from the cord. The acceleration is obviously that way. Now note that W2 has two components as before. One component is perpendicular to the plane and the other one is parallel to the plane. Let's write down Newton's second law for mass m2. The acceleration is down the plane in that direction, so W parallel 2 must be greater than the tension. So the net force on m2 is W parallel 2 minus tension. Now W parallel 2 we have shown it to be 2.5 g times sine of the inclination angle, which is 60 degrees, minus t. So that's your net force. And according to Newton's second law, this net force must be the same as mass of m2, which is 2.5 times the same acceleration. So both m1 and m2 have the same acceleration. So this is equation 2. From these two equations, we can calculate tension and acceleration. So to calculate acceleration, let's add these two equations up. So when you add the two equations up, you will see the tension goes away and the first term will simply becomes 2.5 g sine 60 minus, because there's some minus here, 3g sine 30 equals the right hand side 2.5a plus 3a is 5.5a, which will give you the answer for A as 1.19 meter per second squared. So that is the acceleration of the system. Now substituting this value of A in here, we can determine the tension. So tension from equation 1 equals 3 times acceleration, which is 1.19, plus 3g sine 30, and that's going to be 18.3 newtons. And that solves the problem. Problem 2. For the system shown below, find this angle here, the angle theta, and the tension in the connecting string. So that is the connecting string. Now this force here is 5 newtons, and the acceleration of the system is 6 meter per second squared. So the direction of the acceleration is shown to be that. We know the weights of the masses. This weight is 1 kg, and that weight, the hanging weight, is 2 kg. So let's begin with the free body diagram for the mass on the inclined plane. So that's the mass on the inclined plane, like that. The angle, we don't know. It's theta. It's one of the variables that we want to determine. Now let's look at all the forces acting on that 1 kg object. Of course, the usual one is the weight. Weight is 1 times gravity, so that's simply gravity. And then you have this normal force acting like that. You have tension from the cord. Let's call it capital T. And of course, there is this acceleration that way. Now there are two components to the weight. One is the component of that weight perpendicular to the plane, and component of weight parallel to the plane. Now we are ready to write down Newton's second law. So the net force on this 1 kg object is down the plane because that is the direction of acceleration. And the net force is given by tension plus component of weight parallel to the plane. So we can write it as T plus W parallel. W parallel is quite simply the weight times the sine of the inclination angle, in this case theta. So this component right there is G sine theta, whereas this component is G cosine theta. Newton's second law says this must be the same as ma. M is 1 and the acceleration is a. So that's equation 1. So let's just leave that equation 1 there. Now free body diagram for the hanging object. This object right there. Note that the forces acting on this object is of course its own weight. The mass is 2 kg, so the weight is 2 times gravity. And then you have this 5 Newton force acting opposite to that weight. And then you have this tension in the cord that's pulling it that way as well. And the acceleration is going that way. Since acceleration is downward, the net force on this object, on object 2 kg, must also go down. And that is given by all the forces going downward, in this case only 2g, the weight, subtract all the forces that's going upward. In this case it's 5 newtons and the tension. So 5 plus tension. And this net force must be the same as mass, which is 2 kg, times acceleration. So that is F equals to ma. So let's rewrite that equation. It is 2 gravity minus 5 minus t equals 2a, equation 2. Note that we already know what acceleration is. It's 6 meters per second. So we can use equation 2 to get the tension first. So from equation 2, tension equals 2 times gravity minus 5 minus 2 times acceleration, which is 6. And you get tension to be, which is 2.62 newtons. Substituting this value in equation 1, we can find theta. So tension is 2.62 plus gravity sine theta equals acceleration is 6. So your sine theta will become 0.344, and theta is therefore, it's about 20.1 degrees. And that solves the problem. Thank you for watching.